In this topic, we will discuss the following subtopics: definition of radioactivity, types of radiations, detection of radioactive emissions, nuclear fission and nuclear fusion, nuclear equations, hazards of radioactivity, precautions, and application of radioactivity. Introduction. An atom consists of a central nucleus having protons and neutrons called nucleons, with electrons orbiting around the nucleus. The sum of protons and neutrons is called the atomic mass and the number of protons called the atomic number. All natural elements with atomic numbers greater than 83 are radioactive. However, there are few isotopes of elements with atomic number less than 83 were discovered to be radioactive. If the ratio of neutrons to protons is more than 1, the nucleus is usually unstable. Definition of radioactivity. Due to imbalance between neutrons and protons in the nucleus, there is instability. To achieve stability, the nucleus will tend to break or disintegrate with the emission of energy and particles. This disintegration of nucleus is known as radioactivity. Click on the play Observations. Disintegration is likely to continue further as long as the resultant nuclei are still unstable. Therefore, radioactivity is the spontaneous and random disintegration of an unstable nuclide, an atomic nucleus with a specific number of protons and neutrons with the emission of particles and rays. Radioactive decay. Radioactive decay is a spontaneous and random process in which one cannot predict the nuclide that will disintegrate next and at what instant. To visualize this, play the animation present. Half-life. There is a time period associated with decay of a radioactive substance when the original value reduces to a half. The length of time during which half of the original number of atoms of a radioactive substance or nuclei decays is known as half-life. Different nuclides have different half-lives. For example, the half-life of radium is 1600 years. This means that 2 grams of radium will take 1600 years to decay to 1 gram. Similarly, 1 gram of radium will take the same period 1600 years to decay to half gram. The animation below shows how determination of half-life can be done. Types of radiations. There are 3 types of radiations that can be emitted during a radioactive decay. These are alpha, beta, and gamma radiations. Alpha particle. An alpha particle is positively charged with atomic mass of 4 and atomic number of 2, which is equivalent to that of a helium particle. Beta particles. Beta particles are electrons with a charge of -1 and mass of 0. These electrons originate from the nucleus. They can be represented by gamma rays. Gamma rays is energy emitted in form of electromagnetic radiation. They have neither mass nor charge. The main difference between X-rays and radiation rays is that radiation rays originate from energy changes in the nucleus of atoms, while X-rays originate from energy changes associated with the electron structure of atoms. detection of radioactive emissions, photographic emulsions. All the three emissions, alpha, beta, and gamma, affect photographic emulsions or plate. They darken or blacken photographic films. The emissions effect is observed when such plate is developed. Play the cloud chamber. To visualize this, click on the play button of the animation below. Explanation. The tracks obtained vary according to the type of radiation. Alpha particles cause heavy ionization, rapidly losing energy, hence the tracks will have a short range. Because of their larger mass, they do not change their path in air. As they pass, they cause more ionization on their path by knocking off many electrons. Tracks formed by beta particles are thin and irregular in direction. This is because beta particles are lighter and faster, hence cause less ionization of air molecules. Also, the particles are repelled by electrons of atoms in their path. Gamma rays produce scanty disjointed tracks. The radiation ejects electrons from molecules, and these electrons behave like weak beta particles. The Geiger-Müller tube. It is a type of ionization chamber. To visualize how this device works, play the animation below by clicking on its play button. Observation. When there is no source in front of the tube, the scale records a background radiation which occurs naturally. An increase in the scale reading when radioactive source is introduced is noted. Explanation. When the source is placed in front of the window, emitted radiations or particles enter the tube through mica and ionized argon gas. The negative ions move towards the anode, while positive ones towards the wall or cathode. These ions collide with other gas molecules, causing further ionization. This avalanche effect causes a pulse of voltage corresponding to current flowing and registered on the scale. An amplifier can be used to produce audible clicks through a speaker. It can also be used to amplify small currents from beta particles and gamma rays emissions in the scale. Bromine gas is used as a quencher to absorb secondary electrons, which could ionize molecules and also prevent sparking. Background radiation. In the absence of a radiation source, a GM tube records a background count due to the following: cosmic rays which enter the atmosphere from outer space. They produce radioactive nuclides by collision with atoms in the atmosphere. Radiations from materials in the Earth's crust. Radiations from fallout atomic bomb tests. Radioactivity in our own bodies, and impurities with radioactive substances present in apparatus and surrounding. This count rate should always be recorded beforehand and subtracted from subsequent readings to get the correct count rate. Background radiation. In the absence of a nuclear fusion, the fusing or combining of lighter nuclides to form a heavier one is called nuclear fusion. This is accompanied by enormous energy production. An example of nuclear fusion is formation of alpha particles when two heavy hydrogen isotopes fuse. The animation below shows two heavy isotope nuclides combining. Click on the play button and make your observations. Nuclear equations. The reactions undergone during radioactive decay involve the release of alpha, beta, and gamma rays as well as energy. This may be represented using equations showing the changes in terms of mass and atomic number of nuclei involved. If X is a radioactive element, then it can be represented as in the figure where A is the mass number and Z the atomic number of the nuclide. If X undergoes alpha particle decay, then the mass number decreases by 4 and the atomic number by 2 to produce another nuclide Y as shown. Nuclear equations. In the same way, if a nuclide undergoes a beta decay, the atomic number in the release of alpha, beta, and gamma rays as well as energy. This may be represented using equations showing the changes in terms of mass and atomic number of nuclei involved. If X is a radioactive element, then it can be represented as in the figure where A is the mass number and Z the atomic number of the nuclide. If X undergoes alpha particle decay, then the mass number decreases by 4 and the atomic number by 2 to produce another nuclide Y as shown. Precautions. Due to the hazardous nature of radioactive substances, schools in Kenya have been prohibited from storing them. However, the following measures are recommended as precautions when handling radioactive substances. Radioactive elements should never be handled with bare hands, but with forceps or well-protected tongs. Click on the play button to observe how this is done. For the safety of the users, radioactive materials should be kept in thick lead boxes. Persons using or working with the radioactive sources should avoid long exposure times and be checked regularly by doctor for safety. A badge with photographic plate which can be developed is used to show the amount of exposure every day. Applications of radioactivity. Though radioactivity is hazardous, it has uses that are beneficial industrially, medically, agriculturally, and in carbon dating. Detecting defects and bubbles in metals. The source of radioactive radiation, or preferably gamma rays, is put on one side of a piece of forged metal, while a photographic film is placed on the other end. Play the animation below and make your observations. Observation. When the film is developed, we see the equivalent of an X-ray picture of metal. Bubbles and defects inside the metal can be clearly detected. Radioactive tracers. Radioactive tracers are used to detect leaks in underground pipes. The tracer is fed into the pipe and then a Geiger-Müller GM tube is run above ground along the pipeline to detect any increase in the radiation level and hence the leaking spot. Play the animation below to observe how radioactivity helps in detecting leaking spots in pipes. Determining the thickness of paper. In industries which manufacture paper and plastics, radioactive radiations can be used to determine thickness. If a beta source is placed on one side of the paper and a GM tube on the other side, the count rate will be a measure of the thickness of the paper. Click on the play button to observe how radioactive materials can be used to control the thickness of a sheet of paper. control of static electricity. In textile industry, the presence of static charges can be a nuisance since they can attract dust and even cause fire. When radioactive element is placed in such industry, the radiations emitted will ionize air and the ions formed will attract the static charge. This will neutralize the charges and hence solving the problem due to static charges to a great extent. Medical uses. Gamma rays, like X-rays, are used in the treatment of cancerous body growths. They kill cancerous cells when the tumor is subjected to them. Gamma rays are also used in sterilization of medical equipment. To determine the position of a blood clot in the body, a patient swallows a small amount of radioactive sodium. After a while, the radioactive sodium flows in the bloodstream to all parts of the body. The radioactive sodium stops flowing at the place where a blood clot develops in a blood vessel. A detector is then used to find out where the blood flow stops. Click Next to view a visualization on this. Click on the play button of the animation below to observe these agricultural uses. The movement of traces of a weak radioisotope introduced into an organism can be monitored using a radiation detector. In agriculture, this method is applied to study the plant uptake of fertilizers and other chemicals. Sometimes gamma radiation is used to prolong the shelf life of prepackaged foods. Gamma rays are used to kill bacteria present in food to reduce the risk of food poisoning. Play the animation below to observe how some of these things can be done. Carbon dating. Living organisms take in small quantities of radioactive carbon-14 in addition to the ordinary carbon-12. The ratio of carbon-12 to carbon-14 in the organisms remains fairly constant. When the organisms die, there is no more intake of carbon. The ratio of carbon-14 to carbon-12 therefore changes due to the decay of carbon-14. The new ratio is then used to determine the age of the fossil.